Hello everyone. Welcome to the second lecture video. Just picking up where the previous one left off. We were in the program flow notebook. We had discussed variables and functions, two of the basic building blocks of computer programs. The next thing I wanted to discuss is conditional statements or logic. So, excuse me, sorry. We were dealing with some examples or hypothetical situations when we were talking about functions, where we might want a function to return different output given some input. Sometimes this is sort of automatic. So we had defined the square function, which squares some number. And as we change the number, automatically the output changes, because we have a well-defined mathematical operation that gives different output for different inputs. However, sometimes we'll want to do something slightly different. For instance, say we wanted a function that printed out whether a number was even or odd. So we might start writing the function. We say define even, odd, and it accepts some number. And we can calculate, for instance, a remainder when we divide by 2. So modulus division, that's this percent sign, means divide number by 2 and then keep the remainder, return the remainder. So for instance, 2 mod 2, as it's sometimes called, is 0. 3 mod 2 is 1, 4 mod 2 is 0, 5 mod 2 is 1, because 5 divided by 2 has a remainder of 1, just like 3. So we can see this is useful for determining if something is even or odd. We could simply check if the number mod 2 is 0 or 1. So we could make a function that returns this remainder. But maybe rather than returning the remainder, I want to actually return true or false. So maybe we'll call this is even, and when it's or is odd, let's do is odd. So when this number is 1, we'll return true. When this number is 0, we'll return false. Well then, what we're talking about is what happens if something is the case, some case, right? If the remainder is 1, we do this. If it's not, we do that. And this is a kind of formal logical statement. If something is true, then this. So to deal with these kinds of situations, we're going to introduce if statements, which are the syntax for dealing with formal logic in Python and most programming languages. So in particular, we're going to write a program called test high score that accepts 2 arguments, some player's score, as well as the current high score. And if the player's score is higher than the high score, we'll print out high score, and then set high score equal to player score, and return high score. So I'll talk about this in a moment. So we've just defined this function. If the player score is 83 and the high score is 98, we get back 98. 98 is the high score. And it did not print out high score because the player score, 83, was not higher than the high score, 98. On the other hand, if the player score was 95 and the high score was 93, that would be a new high score. So our function prints out high score and returns 95, the new high score. Now, this is not the clearest syntax for what happened. Typically, for an if statement, we would say, for example, is odd, remainder equals number mod 2. If remainder is 1, return true. If or else return false. So this is the typical if-else pattern. If the remainder is 1, do this, otherwise do this. So 1 is odd, 3 is odd, 4 is not odd. The reason we don't have an else statement here is because we aren't doing anything special if the player score is less than the high score. We don't print anything. We don't have to reset the high score to something else. None of that. So there's no else statement here. You might also see sometimes something a little bit different than this, which is there will be no else statement, and the return will be on a equal indentation level as the if statement. Now, the reason for this is if the remainder is 1, we return true. That number is odd. And then because we returned something, the execution of the function halts. It terminates. The function has concluded. So we never come down here. We only reach that part of the function if the remainder is not 1. So this is not as explicit as if-else, but it is equivalent, and you may sometimes see it. So now if we define is odd this way, we still get the exact same functionality as before. So this is a common pattern. You might see this sometimes. Additionally, most Python variables have something called truthiness. So, for example, anytime you're making an if statement, it must be followed by something that can be evaluated as true or false. So, for example, remainder is either equal to 1 or it's not. This remainder equals 1 is a Boolean expression. So if, for example, number equals 5, remainder equals number mod 2, then remainder equals 1 returns true. This is a Boolean expression. However, many objects in Python can be evaluated as Boolean expressions themselves. For example, 0 evaluates as false, but any other number evaluates as true. Any non-zero number is evaluated as true when it's evaluated as a Boolean expression. So to do another variant on this function, we could say, rather than if remainder equals 1, we could just have if remainder. When the remainder is 0, this will evaluate as false. And we simply skip what's in the body of the if statement. Notice the if statement has a body, just like the function has a body. Both of them use colons and white space, indentation, to denote where the body begins and ends. So this remainder, if the remainder is 0, this evaluates as false. We skip over the body of the if statement and go straight to returning false. If remainder is 1, or really any other number, then we return true. Even more efficiently in this case, not in all cases, but in this case, we could simply return the Boolean equivalent of remainder. But that's not always possible. Often, you don't want to return true or false, but rather you want to do something like, for instance, return the words odd or even, in which case this no longer works. But this truthiness is extremely common in Python. Other things are like none is equivalent to, not return, I want bool. The Boolean evaluation of none is false. The Boolean evaluation of the empty string, a string with nothing in it, is false, while a string with anything in it, even just the space, is true. And often we'll find when things are empty, or null, or 0, that their Boolean equivalent is false, while all other cases are true. Often when we're considering logical conditions, we're thinking about some flow of events based on some proposition. And it can be helpful to draw a flow chart when we're planning our program. So for instance, when we're planning this function we wrote, test high score, we could draw a decision tree. So first we check, is the player score higher than the high score? If not, then we do nothing, and we finally return the high score. If it is, then we print the high score, set the high score equal to the player score, and return high score. And these can really come in handy when we are dealing with more complexity. Drawing diagrams of what you would like to accomplish in your code is a great tool for setting yourself up to write effective code and write code that actually does what you want. It helps clarify in your mind all the steps your algorithm will have to go through. So here's a somewhat more complicated example. It's completely artificial, but nonetheless, it shows kind of the structure of a more complicated decision tree. So here's the decision tree itself. If x is less than 50, we return branch C. If x is less than 50, we check if it's even. If it's not even, then we return branch B. If it is even, then we return branch A. So we first check, is x less than 50? Assuming that it is, we then check, is it even? If it is, we return branch A, otherwise we return branch B. So if x is even, return branch A, otherwise return branch B. If x is not less than 50, then we're considering this else, and we return branch C. And we can see how the indentation structures the flow through this tree. If x is less than 50, yes, next level of indentation. Is x even? Yes, next level of indentation. Otherwise. And then, at the top of the tree, at the same level of indentation as the top, we consider our other branch, our otherwise, our else. So we've got two examples here that are less than 50 and one that's more. The one that's more ends up on branch C. The other two end up on branch A and B, depending on if they were even. So as I mentioned, any of these comparisons, these mathematical comparisons, are expressions that Python interprets as Boolean expressions. They're evaluated to Booleans. So each of these comparative expressions becomes evaluated as a Boolean. Every if statement must convert at the end to a Boolean. We can, of course, build up more complex conditions by combining them with the logical operators and or. And there's a little truth table here to illustrate what these do. So if I require condition A and B to be true, then both A and B must be true. If either A or B are false, then A and B are false. On the other hand, if condition A or B are true, or requires only one of these be true. So when condition A and B are true, A or B is also true. And likewise if only one of them is true. These are very useful operators. And we'll see a lot more of them in the future. And or as logical operators are made available with the words and or in Python, which is very nice. It makes reading logical statements very straightforward. And we'll find as we continue to work with Python, a lot of the language is structured with the intention of resembling plain English. Python is extraordinarily readable as a programming language. So here's and or being used to join different conditions. So we have two variables, x and y, and some mathematical conditions for comparing them to other numbers. So when x is greater than 4, which it is, and y is greater than 2, if x is greater than 7, which it's not, and y is greater than 2, and if x is greater than 7, which it's not, and y is greater than 2, which it is. So this second condition about y is always true, but the condition about x is only true in the first case. So in this first case, both conditions are true. They're joined by an and, so the overall expression is also true. These two expressions are also joined by an and, but the first expression is false. So we have false and true, which is overall false. And then finally we have a false or true, which overall evaluates to true. So true, where they're both true and joined by an and. False, where one is false and they're joined by an and true, where one is true and they're joined by an or. So I've been calling these logical operators because they are the equivalent of arithmetic operators, but in the realm of formal logic. There's one more logical operator we haven't discussed so far, which is not. It is negation. Not true is false. Not false is true. So, not x greater than 7. Well, x is greater than 7. It's 10. So, not true, that's false. Or y less than 7, also false. So both of these things are false, and this whole line will evaluate to false. So you can look through these. One thing I would draw attention to is here we have not x greater than 7. X is greater than 7, so that's false. Or not y less than 7. Y is not less than 7, so this evaluates as true. True or false. We have one true, joined by an or, so this expression is true. We see that here. Meanwhile, a very similar looking expression, not, and then in parentheses, x greater than 7 or y less than 7, evaluates as false. Because this is true, this is not true. So this whole statement evaluates as true. And then we negate it. Not true. So false. So that's something to be careful about. It works a little bit differently than, distribution of multiplication or something like that. Not on a Boolean expression is not necessarily the same as if you had distributed the not on the individual parts of that Boolean expression. It's not distributive. So some exercises for you. Write a function which takes in a number and returns true if it's greater than 10 but less than 20, or if it is less than negative 100. And also, in your own words, I described what this percent sign operator does, but in your own words, explain to yourself, maybe in writing, what's going on with this percent sign operator. So, another major component of basic programming is iteration. Often we'll not only want to do this or that, but we'll want to do something many times. And if you were paying attention in the last lecture, you might say, well, I know what I should do if I want to do something many times. I write a function, and then I can apply that function, and it packages up all the code for what I want to do over and over again, and I'm done. And that's partly true, but it's not the entire story. So for example, we had from the last lecture this function doIt. And the advantage was we could modify doIt, change it when we wanted different functionality. And we didn't have to rewrite all these expressions. You know, we already have this code, doIt1, doIt2, etc. But it's a little bit inconvenient to have to write out doIt 9 times. So that's where iteration comes in. When we want to actually perform a task multiple times with the exact same code, then we use iteration. So the most basic iterative pattern is what's called the while loop. The while loop will continue doing whatever is in the body. It will continue evaluating the body of the loop until the condition of the while statement is false. So we'll create a variable x equal to 0, and as long as x is less than 5, we'll do something. What will we do? We'll print out x, and we'll add 1 to it. And unsurprisingly, we get out the numbers 0 through 4. And then, what happened was 4 incremented to 5. This condition was no longer true, and the loop halted. It stopped iterating. We could set this to 10, and it would go up to 9. One thing to, of course, be aware of with while statements is you may get into an infinite loop. For example, if I comment out this line that I never increment x, x is always 0, and so it's always less than 5, and I'll just try to print out 0 over and over again until my computer crashes. So be careful of the possibility of writing infinite loops when you are iterating using a while statement. Let's see a more practical example, especially one that uses iteration, or functions, sorry. So we'll have a function that prints out the first n Fibonacci numbers. So we initialize some variables, the previous number and the current number, and these are the first 2 numbers of the Fibonacci sequence, so we initialize a count at 2. We're going to print out the first n, so it's important to know how many we've already printed out. So we print the previous number and the current number, and then so long as the count is less than or equal to n, we calculate the next Fibonacci number, print that out, update the Fibonacci sequence, and increment our count. Another version here prints every Fibonacci number below x. And we can see a similar but still different structure. So now, rather than comparing count to some number, we're checking whether the next element of the Fibonacci sequence is less than our upper limit. If it is, then most of the body of the loop looks the exact same. So the first 7 Fibonacci numbers are these, while the Fibonacci numbers below 40 are these. Two different examples of iteration with different conditions. Often we'll need to write different conditions for iteration, and so it's nice to keep in mind how we can accomplish that for different halting conditions. Now, this is fine in these two examples where we know when we want to stop in advance. We know we only want the first n numbers, or the numbers below x. So we've already determined where we're going to stop calculating. But sometimes we don't know in advance how many iterations we'll have to do to accomplish our task. So for example, maybe I am in charge of inviting friends of mine to a party that I'm throwing for another friend. And this friend has given me a list of phone numbers to call, and I'm supposed to call all the numbers and invite them to the party. I don't know if I'm supposed to stop after 10 numbers or 15 numbers because I don't know how many numbers are on the list. I should just keep calling until I get through all of them. So the example we give here are a program that prints out cooking instructions. And we don't necessarily know how many instructions there will be in a given recipe beforehand, in advance. So rather than saying, print out 5 instructions and then stop, we want to say, print out instructions until you hit the end. So we'll make a list. We'll discuss those more in the data structures lecture, but we're going to make a list of all the steps for baking bread. We dissolve salt in water, mix yeast into the water, etc. So here's our step-by-step instructions, one after another. And we also have recipes for making soup or cooking a pot of beans. And all these different recipes have a different amount of instructions in them. The beans recipe is quite short, 4 steps. Soak beans, dissolve salt, heat the water, and boil, and then drain the beans. But the soup recipe has quite a few steps because there's so many more ingredients and more to do. It's difficult to write a while loop with a condition for when to stop here. We would have to calculate the length of these lists, implement a counter, and then check whether the counter is less than the length. But Python has a better solution. We can simply loop over the list itself. So a list is what we call an iterable. We can iterate over it. And we will do so by plucking out, one by one, the items in the list. until we hit the end. So in here we have a print recipe function which accepts a list of instructions, and for each step in the instructions we'll print the step. This is a very nice syntax. It's extremely readable. It wasn't clear just then if I was speaking plain English or reading you Python. So we're going to iterate through this list, and each element of the list, one after another, is going to be assigned to this variable step. And we'll print the step and then move on to the next element. So first, in the soup recipe, is dissolve the salt in the water. So out of instructions comes dissolve salt in the water. It gets assigned a step. We print it out. Then we move on to the next. And step takes on the value boil water. We print it out. Step takes on the value add bones to boiling water. And so on. So step takes on the values one by one in the list, iteratively. And we can see that for any length of list, we have no problem printing out all the instructions. We just go until we hit the end. Eventually, step has no next instruction to take on as a value. And at that point, Python is clever and says, oh, there's no value for step to take on, so the iteration is finished. So just like we have our first n Fibonacci with a while loop, as we had earlier, we could also have it with a for loop. And here we eliminate this counter. We no longer need to count how many terms we've printed out, because we can simply have the counter in the for loop. So range creates a list of numbers between the lower and upper bound. So between 2 and n plus 1, count is going to take on those values one by one, starting with 2, then 3, then 4, up until n plus 1. Now we don't actually use count in any kind of condition or in any way. We really just want to iterate over this list of numbers. And when we hit the end, we know count is equal to n, and we're done. You'll see for loops are far, far more common in Python than while loops. While loops are used in relatively few circumstances. They're used sometimes, but not very often. And despite the fact that these implement the iteration in two totally different ways, their results are the same. Which is not so surprising, given that the bodies of the iterative loops are nearly identical. The only thing that's happened in this for loop is we eliminate incrementing the counter because we don't need that anymore. So as an exercise, you can consider both of these and ask yourself which one is better and why. And there's no particular right answer to this question, but it's worth thinking about. And I encourage you, particularly with this exercise, to go to the WQ-Ask question and answer board start making a, actually what I'll do is exercise from WQ program flow, while versus for. So I put this as a question on the discussion board, and you all can give your opinions. Just fixing the formatting. It's important, as I mentioned in the introductory video, to have good formatting for code. Okay, so if you are familiar with programming, you may have heard of recursion. Recursion is related to iteration. Every problem, every computer science problem that can be solved by iteration can be solved by recursion, and vice versa. But some problems are more naturally recursive than others. Some seem to lend themselves more to an iterative style. Some seem more obviously solved using recursion. So, what is recursion? Recursion is a method of repeatedly performing some task by having a function call itself. So, for example, we can calculate the Fibonacci numbers recursively. And a dead giveaway that you can calculate something recursively is when you have some kind of formula where the ith entry depends on previous entries, or the ith value depends on previous values. So in the Fibonacci sequence, the ith number is equal to the I minus 1 number plus the I minus 2 number. This is the formula for calculating the Fibonacci sequence. So we can apply that in practice. If we want to calculate the first n Fibonacci numbers, then we can do the following. We know if n, if we want to calculate the nth Fibonacci number, we can do the following. We can, of course, if n is equal to 0, we know the answer automatically is 0. That's a given. Likewise, if n is 1, the answer is 1. That's also a given. Those are the first two elements of the Fibonacci sequence, and they are specified by rule, by fiat, by axiom. They can't be derived in any kind of way. You just have to say the Fibonacci sequence begins 0, 1, and then from there on you can calculate the remaining numbers using this rule. And so if n is not 0 or 1, we will return the Fibonacci number n minus 1 plus the Fibonacci number n minus 2. So here I'll actually change the letters here to match what's being used in the function. So if the Fibonacci numbers are, actually let's call them capital F. So capital F for Fibonacci. So the nth Fibonacci number is equal to the n minus 1 Fibonacci number plus the n minus 2 Fibonacci number. So the 7th Fibonacci number is 13, which is what we saw before when we were using iteration. We won't ever be actually using recursion in this course. It's often a little bit trickier to think through how to write recursive code in a way that actually works. But it is worth mentioning, and there are many places where recursion is appropriate. But often it's not super necessary for data science. So, now let's summarize all we've learned in this notebook in a kind of little program. So we're going to use variables, functions, iteration, and conditionals to print out the first prime numbers up to some number n. And we're going to break this task up into subtasks. The base task, the simplest task I need to do here, is to calculate whether a number is prime or not. I need a way to check if a number is prime. So I define a function isPrime, which tests whether or not a number is prime. The number 1 is not prime, but it is sort of a special number, so for that one, I just check is the number 1, and I return false if so. For anything bigger than 1, then what I have to do is check if that number is divisible by any number between 2 and itself. So for any potential factor between 2 and the number itself, if the number is evenly divided, cleanly divided by the factor, then it's not prime. If the number is not 1, and it was never cleanly divided by one of these factors, then it is prime. So that's my isPrime function that will check if a given number is prime. Now I have a print primes function that's going to handle just kind of the output. It's going to handle all the printing. So for each number between 1 and the number n, where I'm going to stop printing primes, I'm going to check if that number is prime, and if it is, then I print it out. So the primes below 42 are 2, 3, 5, 7, etc. So for each number between 1 and 42, I check if it's prime, and if it is, I print it out. Not so hard, but this is pretty dense in terms of incorporating good coding habits. I broke up the problem into subproblems and wrote functions that handle each of them. I could very easily change this to isEven and modify this, and then change this to print evens, but the functionality of print primes doesn't depend on isPrime. I could have an isEven function, and print primes would still work. It would no longer be printing primes, it would be printing even numbers, but nonetheless, separating these subproblems lets us compartmentalize our code so that we can easily modify one piece or another without interfering with the overall machine. It also lets us use the function for other tasks. So not only can I use isPrime for printing out these prime numbers, but I can also use it to make a list of primes, for instance. So for every number in this list, 0 through 19, I'll check if that number is prime. Or, sorry, I'll just create a list, in fact, of whether those numbers are prime or not. So 0, I don't know if this is correct. 0 should probably also be false. But here it says true. But we have 2, 3, 5, etc. So we can reuse isPrime in different applications. I'm going to skip this and we'll come back to this in data structures. One final thing to emphasize is remember I discussed the idea of scope. When we have arguments, the scope of those arguments is the function where they are defined. And so I said we don't need to make the name match what the input will be. But even stronger, more strongly stated, the names inside the function, names that are defined inside the function, override the meanings of names defined outside the function. And it's only if a name is not defined inside the function that we go looking for that name outside the function. So for example, I have print this and I have an argument a, and I print out that argument. And I can set a to 5, call print this on 2, and I get 2 as output. It didn't matter that a was set to 5 outside the function because the scope of this name a is the function, and it overrides this a, which is in what's called the global scope. However, if we don't define a as an argument, then a isn't and we don't, say like a equals 2 or something, then a is not defined anywhere in this function. And so when Python discovers, oh, I don't know what a is in this function, it's going to default back to the global namespace where a is defined. And it will find a is equal to 5. I highly recommend reading this over. This is a very subtle concept that often trips up students new to programming. In short, I would recommend the following. Whenever you are defining a function, think about what its input should be. Give that input a name. If you don't use that input in your function, alarm bells should go off in your head that something has gone wrong. Additionally, if you use a name inside of your function, if you use a variable inside your function, and it's not defined as an argument, alarm bells should go off in your head. And it might be totally fine, but you should always remember that problems can originate from these places where we haven't used inputs, or we've used a name in the function that's not defined in the function. This is a very common source of errors for students. I'm going to actually skip the remainder of this, but you should you can study it on your own. We're not going to make use of function closure very much, although it is a powerful technique. It's a little bit advanced in terms of programming, and doesn't always see a ton of use in general contexts. But if you are interested, it is here for you to study. We will not, nor do we have time, to go over every single thing in every single notebook. So you're going to have to take initiative on certain components of the course material and engage in independent study. So I'm going to wrap up lecture here. I'm a little bit late for office hours, and I'll catch you in the next video.